you need to have constant time O1 access to the IF element in that list. So it can be at any point. You shouldn't have to go from the start to the IF element. You should be directly able to index the IF element. So that's essentially binary search. Right. So moving on to the description of trees. Trees are essentially one of the most important data structures, and you'll be looking at these throughout in the course of your computer science degree, as well as when you go into professional lives and you're working in software engineering jobs or handling data. Trees are very prominent sort of data stores, and we'll look at why are they that. And one of the greatest things that they offer us is that they offer O-log event operations, right? So you can search things in logarithmic time. You can traverse the tree in logarithmic time. What does that essentially mean? So take an example of Amazon. Amazon currently has 350 million products in its complete database, right? So that's a huge number. And then if you were to look up any product, if you went to the Amazon search bar and typed in, you wanted to, let's say, look up, new sneakers that came up or something, you when you type in, it only takes a maximum of 29 steps to traverse. So within 29 iterations, you're searching through 350 million entries. Now that's a huge amount of data being searched in a handful number of iterations. And that's one of the greatest benefits of trees is that when you're working with large data, when you're working with scalable data, it just becomes very easy and efficient. And if you were to do it 350 elements inside of a list, or some other data structure, it wouldn't be that efficient. Amazon wouldn't be what Amazon is today if they didn't have these efficient data structures where they were storing their information. Any questions so far? All right, so some other data structures that, we have arrays. Look at arrays. Arrays are simple. Trees, we'll talk about this. Hash tables. So hash tables are slightly different from trees. Hash tables also provide constant time access to an element, and they don't necessarily have to be sorted. And what hash tables do is that they take the key and they hash it, and then instead of searching for the actual key, you're searching for the hash. And that's how, because hashes are unique, you get constant time access to hash tables. I'm not entirely sure if hash tables is covered in 251, but maybe databases might be coming up at some point. And then graphs. So graphs and trees look similar. They have similarities, but they also have their own unique differences. And one of the unique differences is trees sort of have this hierarchical, whereas there's a root, and then there's branches. There's a graph. There's no set pattern or order where you can have different nodes connect with different nodes. Questions? So a good example of a graph would be, like looking at, a social network graph, or, like your Facebook friends and their connections and then their connections. So you can have like nodes as actual people and edges as actual connections. So there's no essential hierarchy there. So graphs don't essentially have such element of hierarchy, whereas trees we'll look at do have a hierarchy. All right, so talking about continuing on this discussion of how Amazon is huge with 350 million products in its database. So what happens behind the scenes when you type in something in the Amazon search bar? So the very first level, what happens is that your product it gets formed into an actual database query. So in this case you're doing select all from products. You're selecting something from the database products, right? And that query gets sent over to the Amazon server. Now there's the Amazon web server and there's also Amazon the database server. That web server forwards that query. It looks at, okay, this is a product query. This is for data that's stored in the database. So I'm going to send this query over to the database server. Now, what happens when the database server gets that query? The database server is essentially that where all the actual database is stored. And then the database server essentially executes that query. And the form in which the data is stored is some sort of efficient tree, right? So essentially, that essentially allows us to search for it in an efficient manner, in a faster manner. Any questions up to this point? All right, so this is a question for you. We don't have clickers today, so don't worry about those. Sir, you have a question? You could have a graph that is also satisfies the properties of a tree. I'm not entirely sure. What do you mean encode? Right. Yeah, you could do that. You could. There are methods of converting information in a graph and information in a tree, but it really depends on what's the use case. So yes, so please feel free to discuss with your peers. I'll give you a few minutes to go over this question, and then we'll discuss it collectively. Right, so is this a binary search tree? If not, which node is incorrectly ordered? You get a handout? You get the handout? Yeah. Yeah. Enough time today. class. So let's come back and discuss. So because we don't have clickers today, we're going to do a raise of hands. So how many people think that this is a valid binary search tree? Raise of hands. All right. Is that a yes or no? All right. So how many say no? All right. How many think B is the correct answer? All right. And what about C? All right. Yeah. So yeah, the majority are in this case is correct. Yeah, C is the correct answer. This is not a valid binary search tree. So if we look at the structure, I mean, it looks like a tree. One of the requirements and properties of a tree is that the nodes, the keys, which are essentially stored in the nodes themselves, need to be ordered in some sort of fashion. You know, so in this case, because these are names, they're supposedly have to be, for it to be a valid binary search tree, they need to be ordered in some alphabetical order, right? So if you look at the root node, you've got Chen, right? So everything that's smaller than the alphabet S should be towards the left of the tree, and everything that's greater than the alphabet S, it should be right of the tree, right? And we come here, we look at the node Yanlin, which Y, it seems in place, but when we look at the leaf node here, Ragib, it's out of place, right? Because R is less than, R comes before the alphabet S, but in this case, the node is towards the right of the tree. Everyone clear on why this is not a valid binary search tree, and what's the problem here? Any questions before we move on? All right, so if I were to convert this into a binary search tree, where would I move, or Gabe? Where would that go? Yeah. It would go on the right of E. Exactly. So yeah, so it would come out here. So the reason why we can't put it here is because R is greater than A. So it can be towards the left Amanda. It has to be the right of Amanda, and we've got Lee here, and R is greater than L, so it's going to be towards the right. So it's going to come out like something like select right here. So in this case, it would become a valid binary search tree. All right, another question for you guys. Again, is this a binary search tree? If this is not, which node is incorrectly ordered? Feel free to discuss. It's a So let's come back. Let's see. So how many people think that this is a valid binary search tree? Awesome. How many people for B is the correct answer? All right. Yeah. So in this case, it's not a valid binary search tree. The node 54 is out of place. Right. So like we mentioned, that everything that's greater than the root node should be towards the right-hand side of the root node. And in this case, 54, it's greater than the root node and it's towards the left. So everyone understands why this is not a valid binary search tree. Okay. So if we were to create this, we would have to move 54 to the left. 54 would come out right here. It's where. Maths is acting all weird. Okay. But you get the point. Any questions? All right, so question for you all is, now that we've looked at some examples that were not binary search trees, and we understand what are essentially the properties that hold for a binary search tree, your task here is to create a binary search tree, and you want to follow this specific order. So you want to insert in this downward order. So mom gets inserted first, followed by dad, brother, sister, and so on, right? So the insertion order is important. Take a few minutes to draw this on your handouts or on your sheets, and then we'll go through a visualization in which we'll develop this tree step by step. Yes?
Is that alphabetical order, or just like?
Yeah, yes, alphabetical. Alphabetical. So you'll be using, like we looked up in the first example with names. Yep. Well, it's a tree. So in case of a tree, you have to follow that property that it has to be sorted, right? In this case, you're going to start with your first node is going to be your root node, right? So in this case, mom is going to be your root node, and everything is going to get sorted with reference to mom, right? But yes, you just can't go down a straight line. Then it would just essentially be a list. It has to have some sort of hierarchy. So things that are greater than the letter N should be on the right side. Things that are less should be on the left side, and then go so on and so on as you go down the nodes. Yep. Question or okay. Yeah, feel free to discuss. And you've got take 2 more minutes, and then we'll cover this and through a visualization. class. So let's come back and see how this tree would be formed. So starting off, also this link should be available in the class slides. So if you want to go ahead and after class you want to do some visualizations of trees and see how trees are formed, it's a useful link. So first node, mom. So insert. There's nothing in tree. You've just got one node, right? So the first node is your root node, and everything else is going to be sorted along the root node. So second node is that inserted. So D, because the alphabet D is smaller than the alphabet M, it it branches onto the left-hand side. So brother. Because B is less than M and it's also less than D, it comes to the left-hand side of Dad. One thing you want to note is every time you're inserting, you start off at the root node. So that's one property of inserting is you're always going to start at the root node. And we'll also look at how this is implemented in code when you do it through pointers and stuff. So where would sister, when we implement sister, where would insert sister, where would this, it would be on the right of mom. Correct. And cousin, comes out here, grandma. Now where would grandma come? To the right of brother. So G is, it would be on the right of dad. Let's see. Yep, there you go. So because what happened here was G is less than M, so it comes onto the left-hand side, but when it comes onto the next node and it performs the comparison, is the first alphabet's D, and then the alphabet in comparison is G, so G is greater than D, so anything that's greater goes to the right-hand side of the tree. Everyone clear how this whole insertion process is working? However, we're starting off with our root node, we're doing a comparison, we're moving on one level deep, we're doing a comparison again, and we're moving on. And you can also see how this is very similar to binary search, right? In terms of binary search, what you do is, you pick up from the middle, you compare from the middle. If it's smaller, if it's greater, depending on that, you pick half of what's remaining. So every time you're reducing your search space into half. And sort of in the tree, you're doing the same thing. You're picking up, you're leaving out where everything's on the side that you don't look into. All right, so last one, aunt. Aunt's gonna come out right at the very beginning. Right here. There you go. All right, so we know that this is a valid binary search tree. It does it only lets me type in alphabets of 4, so you get the gist of it. So does anyone see any issues with this at all? Exactly. So I know you haven't covered balanced and imbalanced trees, but this is something we'll cover on later. But just to get a basic idea is when you're looking at this tree, what it means to be balanced is that there's roughly everything equally distributed. In this case, it's not, because if you look at the left of the root node, you've got 5 nodes, and right of the root node, you've got 1 node, right? So essentially, it's not a problem when you're working with, like 8, 10, 12 nodes. Well, let's say you've got thousands and thousands of nodes that you're working with. And then you insert them, but the tree's not balanced. It means that on a random search, when you're picking some element to search for randomly, it's likely to be half the time on the left branch and half the time on the right branch. Now, if your right branch is smaller, it's like your left branch is heavier, it's going to take longer. So it's not going to bounce. If it comes up in the right branch, the search is going to be really fast because there's only going to be depth. It's going to be 1, 2, 3. But if it comes down to the left branch where you've got all those nodes, it's going to take more time. So we want to optimize the overall efficiency of a tree, and that's why we do the process of balancing the tree, where we rearrange the nodes, we rearrange the root so that it sort of spans out in a balanced fashion. Yes, question? Mm-hmm. Right. So when you come out of the root node, you compare, right? So you perform a comparison of what the key you're searching for and what the key at that node, specific node is. Now, if that key is lesser in value, you go towards the left. If it's greater in value, you go towards the right. So you're only doing a comparison at each node, and depending on the value of that if conditional, you pick the left and the right. And we'll actually look at this later in the lecture today when we look at the actual implementation of the search code of a binary search tree. That'll clarify things. Any questions about the tree itself, the insertion process before we move on? All right, so that's the link we were using for the visualization. All right, so let's see how a binary search tree is implemented in code. So this is an example you've got of a binary search tree. So you've got the class, it's named binary search tree. It's got private members. So the private members are the node struct. Now, the node struct essentially represents each individual node. And you've got 3 elements in the struct. So you've got the key element. The key element essentially stores whatever the value is, right? So it's a template, so you can have ints, you can have strings, you can have whatever. In this case, this is a binary tree of integers. And then you've got 2 pointers. Now these pointers are of type node, right? And then visualizing it, these pointers, one of these pointers points to the node that's towards the left, and the other one points to the node towards the right. Any questions? Then you've got also the starting point, the root node, and then you've got the size of the tree. And then in your public members, you've got the default constructor, which is the binary search tree constructor, and then you set your root pointer to null and the size of 0. So when you execute this line right here, so you're creating a binary search tree of type integer and the variable named tree. Right? So tree is going to have the root set to null and the size set to 0. And then you're going to go ahead and do the insertion process, and that's going to populate the tree. Any questions about the tree class, the code and everything? Does everyone understand why we're setting the root and size in the default constructor? So the default constructor essentially gets executed when you create an instance of the class, in this case, and then you everything that you want to initialize it, you set in the default constructor. And that's why we're setting the root to null, and we're setting the size to 0. Because the tree, it's just a tree, it's not pointing to any nodes. We haven't inserted any nodes in it. So this is what your tree initially is, but the size is going to be 0. But as you populate it, every time you insert a node, the size, you increment the size, you do size plus 1 with some function inside the insert method. Any questions? Yes. I'm sorry? Yes, we haven't looked at insert yet. We won't be doing it in class today, probably Wednesday. We'll look at search next. But yes, insert is similar to inserting in any like sort of linked list and stuff. So if you look at the structure of the class, does it seem familiar to any other data structure? Like perhaps when you have like linked list, a doubly linked list, you give the left and right pointers. Have you recurred that in any of their course linked lists? Right. So yeah. So it's kind of similar. We're using pointers. We're using efficient memory allocation and storage, but it's better not to to think of it as different as a linked list, because I had this question where like the nodes you could do previous and next, but when we're looking in terms of trees, it's ideal to think of terms of left and right, because that's how it just becomes very easy to visualize it, because in the tree, everything on the root of the node, there's no previous and next, because it's a hierarchical structure that goes down. There's left and right. Any questions? Yeah. Two equal nodes. That's a so because they're used for search, essentially, when you try to overwrite a node, it won't. It might just already exist. So it won't really insert if it's already present in the tree. Right. In that case, every product in that case is going to have its own unique. Even if the name is same, it's going to have like different identifiers. So every node in the tree is going to be unique, right? So good question, because when you think of it in like practical terms, you see okay, like Amazon has like hundreds of products that sort of map to the same thing, and different sellers having same products at different prices and all that stuff. But how does that get sorted? So so they're not essentially using the product name; they're using the key. And one attribute of the key is that it has to be unique. So all those products, even if they have the same name, the same manufacturer, they're going to have unique keys, right? So that's usually some random string, and they're storing it in the form of that key, is how they're populating that tree. All right. Any other questions before we move on? All right, so quick task for you is you've got the same tree that we just looked at. You're searching for the key 40. Trace out the path searched, highlighting the edges traversed, and circling the nodes visited. So I'll give you 3 minutes to complete this, and then we'll collectively look at it over here. For those of you who don't have a handout, just please use a scrap pen and paper and just draw the tree. Good practice. Alright, so people still work on it. I'll give you 1 more minute, so then we'll look at it. All right, class. So let's come back and see how we're gonna go around this. So the key you're searching for is 40. So every time you want to search for an element in the tree, you start off with the root node. So you're gonna go up to the root node. What's the key at root? 22. So 40, you're gonna do a comparison. So is 40 greater than 22 or less than 22? Greater. So if something's greater, then you go to the right side, right? So we're gonna circle this. We looked at this node and we go to this edge. The next node is 49. Now we do another comparison. So 40 is less than 49. So in this case, we go to the left side. Great. So we go out this edge. Then we come at 35. Now 40 is greater than 35, so we're going to go again to the right side. And now we've hit 41, right? So what happens here? So what, in terms of implementation, when we come up here at the leaf node, we compare 40 with 41. It's smaller, so we should ideally go to the left side, right? But is there a left side? No. So the pointer here would be null. So that's how you know you've hit a leaf node, is that the left and there's not going to be any left and right pointers, right? But even if there was, this is not a leaf node, and there was some element here, let's say 51 here, even in this case, because 40 is less than 41, the left, and there is no left of 41, so it's still going to be null, right? So when you've hit null pointer, that means you've traversed the tree and you haven't found that element. So in the case you haven't found it, you return not found or return false or -1 when you're implementing your search. So this was a broad abstract implementation of search. Now let's look at the code for search. So same exact tree, same implementation of the binary search tree class, and we've got the search. We're providing the key that we want to search for, right? So it takes in one argument. Currently, your current node is set to the root, right? So whenever you initiate search, you're going to start at the root node. And then we're going to increment the current pointer, and like I said, you stop when you hit null. So when you hit null pointer, that means you've traversed the required path in the tree, and you haven't found that element. So when there's a search process, you're doing the comparison. You're checking the key is equal to the key that's stored at that node, return true. This means you found that key. But if you haven't found that key, if it's less than, then you go towards the left. So this is where you're updating your current pointer to point to the left node of that current pointer. So you're updating current. And then if it's greater, you're updating current to point to the right to the pointer. Right? So you've got the tree implemented. You're just moving the pointers to traverse through the tree. And then if you hit null pointer, like if you hit, like in the search example that we saw, you hit null and you didn't find that certain element, you just return false. Any questions? All right, great. Thank you. That's all for today. I'll see you all Wednesday. Reminder, you do have homework that's due on Wednesday at 5. Homework 5 that's due Wednesday at 10 a.m. Thank you.